In this video, we're going to look at logarithms and logarithmic functions. Suppose we start with a positive number b, we'll call that our base. We'll start by defining log base b of x this way. So think of x as an input to this log base b function. But log base b of x is the exponent you must raise the base to in order to get x. And I think it might initially be good to think of this as a question. B to what power is x? Because when you determine that, that's the output from the log function. So for example, if I want to know what is log base 10 of 100, well, I ask myself the question, 10 to what power gives me 100? And of course that power is 2. So log base 10 of 100 is 2. Let's try another one. What's log base 4 of 64? Well, what's the exponent I have to raise 4 to get 64? 3. So log base 4 of 64 is 3. One more. Log base 9 of 1 over 81. Well, yeah, 9 to the minus 2 is 1 over 9 to the positive 2, which gives me 1 over 81. So log base 9 of 1 over 81 is negative 2. Now, the base 10 is a special base, and a lot of calculators have a log base 10 button. Sometimes it's written just log, assuming the user knows it's base 10. There's another special base out there, and it's base e. This is an irrational number. It's approximately 2.71828. It comes up in a lot of applications, a lot of the sciences, and so it's also given a button on calculators. It's not written log base e, rather ln, called the natural logarithm. So for example, what would be natural log of 1 over e? And again, think of it as a question. What would I raise the base e to get 1 over e? And of course, I would raise it to the minus 1 power to get 1 over e. Okay, so that's one way to think about logarithms. Let's think about them graphically. So let's take y equals log base b of x. Think of it as a function. You give me your favorite x, and you get an output y. Now, one thing is, for any b to the power 0 is 1. So what's the equivalent logarithmic statement? That means log base b of 1 is 0. So we've got at least one point graphed, right? When I plug 1 in as an input as my x, my output y is 0. So there's one point on the graph, and that would be on the graph no matter what b is. Now let's think about taking inputs which are to the right of 1, getting bigger to the right. So we've already seen that when we plug 100 into, say, log base 10, we only get 2. What would be log base 10 of 1,000? Well, wouldn't that be 3? Because 10 to the 3 gives me 1,000. So it turns out the logarithm function is going to grow as you go to the right, but very slowly. Now, what about to the left of 1? You can't plug 0 or anything negative in. It would make no sense. But what about numbers between 0 and 1? Well, for example, log base 10 of 0.01 or 1/100th is negative 2, right? Because 10 to the power minus 2 gives me 1/100th. So that means as I take values to the left of 1, I'm getting negative values. And so when you put all that together, the logarithm functions are shaped basically like this. Let me draw it here. They're negative to the left of 1. They go through the point 1, 0, and then they grow very slowly this way. That's all about logarithms today.